fancy word for the normal scale. Okay, so if anybody's kind of saying what the heck does that mean, that's just the normal. I'll put it in quotes because that's probably the technical term would be rectilinear. So we're going to plot that, plot the data. When you plot the data, if you get a straight line on a rectilinear scale, then you know that you have a linear function. And that was what we got in the cantilever beam example. Now, the next step here, if you don't get a straight line, then you can go on and check if you plot it on a semilog scale, what do you get a straight line? And if you get a straight line on the semilog, then you know that it's an exponential function. And likewise, if you don't get a straight line at that point, you can move on to the log scale, and if you get a straight line at that point, you would have affirmed that it's a power function. So basically, plot the data back at step 2 here. If you plot the data using the rectilinear scale, if you get a straight line, then you know it's linear, and you would theoretically stop. If you plot it on a semilog scale, if you get a straight line, then you know that it is exponential. And if you get a straight line when you plot out log, then you know it's a power function. So, not exactly rocket science, but there's just kind of these 4 steps, and it's just sort of, again, it's not really rocket science. Just kind of take your time through these steps of once you have the data and plotting it to figure out what type of a function you have. And once you know the function, then the next step would be to obtain the coefficients, which is what we're going to do on the next slide. So once you've got the data, you've plotted it, and you've got a straight line. So you either have your normal axes, or you've gotten some combination of semilog or log-log axes. If the data falls fairly close to the line, and it's a pretty good approximation, then you can follow these steps that we're going to go through right now. If the data is kind of scattered around and there's not really, or it's difficult to identify a unique straight line, then you're probably better off going through and using the least squares method, which is what we're going to go through in the next lesson. So, excuse me, if the data is fairly close to the line and it's a linear function, and you've kind of determined from the previous analysis of the data that it's linear, then you can figure out the slope of the line by comparing 2 data points that are on that line. So m equals y2 minus y1 divided by x2 minus x1. So the one thing to kind of point out here is if you've got your data, and let's say that you've got it, and I'm just, scattering out data here. So let's say this is your data, and you plot your line, you take your straight edge, and you plot it through here. When you're taking these data points to calculate your slope, you're not taking the data points from your measurements. You want to actually take data points off of the line that you're using. So here, I'm going to change pen colors. Alright, so now I got the orange pen. So you would want to use points off of the actual model that you've developed, and that model is that straight line. So that's where you're getting your y2 and your y1, is reading it directly off that line, not off the data that you used to determine where that line should go to. So the axis, or the y-intercept would be determined from picking one of those points and calculating y minus, that's a subtraction sign, m, and then x1. So you can take any one of these points, again, off of this line, and once you've calculated this slope, you would use that in the next equation here. So again, pretty trivial stuff, but worth having in your notes at least. So for a power function, once again, you would do the same thing. You would have plotted these out. Now with the power function, if I'm just going to use the same axis or same plot again. So this time you've got log of y and log of x. Or if you just plot it on, you could plot your normal y and your normal x on a logarithmic scale. But you end up with wherever you have those wherever you have the line, pull off your points. So you end up with the first data point that you pull off, your bx1 to the m, and you've got y2 is equal to bx2 to the m. And so this y1 and x1 is just a corresponding set of data points that you've pulled off of your model. And if you merge the two of those together, you can get m is equal to the log of y2 divided by y1 divided by log of x2 divided by x1. So by solving these two equations simultaneously, we can get this. And then the y-intercept would be solved just by manipulating that equation around to get the b, and you can use either one of those data points, that y1 times x1 to the negative m. And so again, you're substituting in this m value that you calculated into the second equation to be able to solve for b in much the same way you did the linear function. The exponential function, pretty much the same thing. You end up with y1. You can set up an equation for b, and then we'll use this one as the log 10, but you would do the same thing for the natural log. M x1, set up a second equation, y2 is equal to b times 10 to the mx2. And you would solve the two equations simultaneously, so you get your m value. The slope is equal to 1 divided by x2 minus x1, and log of y2 minus y1. So if you're looking at where did this equation come for the m, if you manipulate these equations around, you should, using those the properties of the logs that was on one of the first slides in this lesson, you should be able to come up with that equation. And then same way, you're going to solve for b using one of the sets of values, and 10 to the minus m x1, and you can get your b value, again substituting in this value of m that you calculated. So if the data is close to the line, you can use this kind of mathematical approach, but if the data is scattered and you're not really sure exactly where that line is, you're going to use the least squares method to calculate. So before you go on to the next lesson, I'm going to, kind of separate from this, I'm going to have problem number 1.18. I'm going to solve that in a separate video since it'll take a few minutes. But I'd like you to sit down and try to go through example 1.41 and 1.42 out of the textbook on your own. And basically all that's doing is it's showing you a practical example of how to solve a problem where you identify the function and then determine the coefficients for the model. So if you go through 1.41, 1.42, and then I'll solve through problem 1.18 from the back of the book, or the back of the chapter, as another kind of like in-class example. So that's all for now. If you have any questions, please feel free to post on the Carmen site or get in touch with me, and I'd be happy to explain any of this stuff. So thanks, and have a good night.